So uh, recording has been started, and just for confirmation, can you all see the screen and hear me? I just need a quick confirmation.
Yes,
Yes,
sir.
Bhaiya.
You can't see the screen?
Yes, we can see.
Okay, very nice. Perfect. So let's begin the session. So yesterday we did quantum mechanics, little bit of quantum mechanics, understood the laws of quantum mechanics using the infinite potential. So let's quickly recap what we did yesterday. I said that the infinite quantum well is a is an ideal situation, is an ideal case, and we define this as that potential whenever the potential is zero within some range, let's say 0 to a, and it is infinite everywhere else. So your particle is inside this well and it can't go outside. The reason being because outside the potential is infinite. So the if a particle is in the infinite potential region, its energy will be infinite, which is not possible. So this is what we dealing with, that our particle is within this small region, 0 to a. Usually in quantum mechanics, this a is very small in the terms of nanometer or even less than that, angstroms or Fermi meters, something like that. Depend upon whatever the problem we are dealing. In quantum mechanics, whenever you want to decide your system, whenever you want to study your system, you have to define the potential. So in this case, potential is defined as zero within this region and infinite everywhere else. Then we talked about that particle is inside the well and we want to study the different things about this particle. So what we do is we find the possible values of energy this particle can have when it is inside the well, and what are the energy eigenstates. What do you mean by energy eigenstates and energy values? For example, very simple thing is, you know that quantum hydrogen atom. So you know that hydrogen atom can have many energy levels. We say n equals to 1, n equals to 2 energy. So when your hydrogen atom, so we define that hydrogen atom has energy like this, minus 13.6 electron volt divided by n square. So these are the possible energy levels. Similarly, we want this possible energy levels for our case for infinite potential. Now in quantum mechanics, we also need one thing, that if I say that your system is in your particle or your hydrogen atom is in ground state, that is n equals to 1, your energy is minus 13.6 electron volt. But how do you describe the system? We describe the system by energy eigenstate, or called wave function, by the wave function. So we say that when a particle or when a system is in this energy level, then our system has this wave function, or we can define the state of the system by this energy eigenstate. So in quantum mechanics, we do not define particle or wave. We say it is a wave function. So electron is a wave function. Any quantum system is defined by a wave function. We do not talk about a particle or a wave analogy. Okay. So similarly, here we are decided to. So how do you define these possible energy levels and energy eigenstates? We define it by using the Schrodinger equation. This is a Schrodinger equation, time independent Schrodinger equation. We solved this equation and used the boundary condition, which was very important. We used the properties of wave function and the boundary conditions to find this energy levels. And we actually found that if a particle is inside the well, it will have this possible energy values. Now, you will be a big idiot if you don't remember this. Okay, you have to memorize this. This formula you have to memorize. Okay, very, very important formula. You should mark it. And also you should know that n starts from 1 and it can take value 1, 2, 3, 4. Okay. Then we said what are energy eigenstates. So it means if your system is in energy, have the energy E1, it will be defined by an eigenstate I1, phi1, energy eigenstate phi1. If it is by E2, we define it by phi2, and so on. So what are these phi1, phi2, or in general phi n? It is under root 2 by a. What is a? A is a length of this box or dimension of this box, 0 to a. So under root 2 by a sine n pi x by a. N you can put and you can get phi1, phi2, phi3, phi. So now comes the big question. Very important question. So now we will have the various discussions which can actually come as a direct questions in the JAM, CUET, GATE. So number one question is, what is the ground state energy of a particle when it is inside the this potential zone? So we just put n equals to 1 and we get pi square h cut square 2m. What is the first excited state? We put n equals to 4 pi square h cut square by 2m square. Or we can simply say it is 4 times the ground state energy. Similarly, E2 is 9 times the ground state energy. This we can easily get. For you is, and you have to answer this question. It's a very important question. So one energy levels I have already drawn. So ignore the plots. So ignore this for a while. One energy levels I have already drawn. Now I am drawing the second energy level. So let's see who can identify this. There are two energy levels. Red is for one particle and black is for another particle. So you need to tell me which one is for electron and which one is for proton. Means one energy level out of means either black is for an electron or either red is for electron or vice versa. So you need to tell me which one is for electron and which one is for proton. It is all written on your screen.
Red for proton.
Red is for proton. How many of you agree with this person? Who says red is for proton? Only one person says other. What the other feels? Opposite. So why? Who answered? Tell me why red is for proton.
Proton has more mass than electron, and the mass term is denominator.
Yes. Yes. So you can see that in this formula you can find that the mass of a proton is more. So E naught will be less. That is why red. This will be the for the proton and black is for the you can say electron. Okay, so this was the first concept. So heavier the mass, lower is the ground state energy. Okay, so let's say now I talk in terms of human. If I put a human inside it, so your ground state energy will almost become zero. It will almost become zero. Okay, so some other things I want to discuss here is the separation between levels. Means the two levels, on what factors the separation between the two levels depend upon. Number one is A. What is the dimension of the box? If the dimension of the box is too big, means very, very large, then the energy levels are almost continuous. They are very close to each other. Why? Because E naught becomes very, very small. What is the energy difference between two levels? It is like this, na? E1 minus E naught. If I do, what I will get? 3 E naught. So it depends upon E naught. So the energy difference between two levels depend upon E naught. E naught is pi square h cut square by 2m. It inversely depends upon A. If A is very large, then your energy levels are very close to each other, and energy levels are almost continuous. Second, mass. If mass is very heavy, like humans, for example, so energy levels are again continuous. So we do not see the discrete energy levels. We see the continuous energy levels. Okay, that is a reason that we are quantum mechanics deal with the small. If you want to see the discrete energy levels, you have to go small mass, small dimensions of A. Rest other things are constant. Pi is constant, h cut is constant, and A is constant. 2 is constant. You cannot change them. One knowledge was this. Now comes the second knowledge. So let's say you have to, it can be asked in the exam, and it has been asked many times that draw the wave functions. So what is a ground state wave function? Ground state wave function is root 2 by A sine, put n equals to 1, so we will get sine pi x by. So ground state wave function will be this. So when your particle inside the box has energy E naught, it will be described by a wave function which can be plotted like this. Similarly, for first excited state, your wave function is root 2 by a sine 2 pi x by, putting n equals to 2. So it is like this. Similarly, for n equals to 3, you get like this. We have to make some very physical observations from this. Number one physical observation I want you to make sure is nodes. Number of nodes. Nodes is a thing, okay, where the probability amplitude is 0 or probability is 0. So what is probability amplitude? It is wave function phi. We discussed it yesterday. And what is probability? It is phi star into phi. Okay. So wherever the probability amplitude or probability is going 0 is called nodes. So we do not consider the endpoints 0 and 8. We will not consider, because it is very compulsory for wave function to go 0 at the ends. We discussed this yesterday. Why? Because wave function is 0 outside, because particle can't be outside. That is a reason that on boundaries also the wave function needs to be 0, so that wave function can be continuous. So that was something which we discussed yesterday. We need to see the points inside the well that do it gets 0 inside. So yeah, no, if it is in ground state, there is no point inside the well where it goes 0, where probability of finding the particle is 0. No, nowhere. Similarly, for first excited state, there is only 1 point. For second excited state, there are 2 points. So number of nodes is equals to n minus 1. If you put n equals to 1, you will get 0. If you put n equals to 2, you put 1, and so on. So this is also called node theorem. Node theorem. Okay, so remember this. This is also called node theorem. Second very good observation we have is, what does this node theorem actually represent? So it is a very good representation. So if you are in first excited state, let's say this, your particle is in first excited state. What does this mean? How do I see quantum mechanics? Most of you will be seeing it like a wave, that this particle is like a wave which is in entire box. No, this is a very wrong description. How do you see this wave function? So let's see this wave function along with me. So let me remove all this and now see this wave function along with me. Remember that phi is a probability amplitude. It is not describing how your entity is inside the well. It tells you about the probabilities. So it tells you that probability to find the particle at this point, let me change the color of the pen, at this point, means at this x value is maximum. At this point is also maximum. Okay. And at this point it is 0. In the middle it is 0. What do you mean? Let's say your particle is in, I'm again and again saying particle, but don't consider it like a particle, and instead quantum entity. Let's call it as quantum entity. So the probability to find quantum entity, if you are making the measurement of, and if you are trying to look up your quantum entity, most of the times you will find that your quantum entity is placed here when you will actually observe it. So most of the time after observation, you will find that your quantum entity is here or here. You will never find your quantum entity in the middle of the well. So can we relate it with the concept of simple pendulum? Yes, we can. So let's try to analyze it. So this is our simple pendulum. It is oscillating like this, like this. You know that maximum speed. So can anyone tell me, while oscillating, where is the maximum speed of this mass of this bob? Where will it have the maximum speed?
at mean position.
Yes, at mean position, this mass has a maximum speed. So when the place where the mass has a maximum speed, and if you are trying to see this pendulum, okay, and let's say you are clicking the photos of this again and again, you are clicking the photo. In each photo, you will see this pendulum at one spot. The place where the speed is maximum, there is minimum probability that in the photo you will be able to capture that place. Why? Because speed is very fast, so mass will quickly get through it, so you will never be able to see that mass at that spot. So but there is 1 in million chances that yes, maybe it can happen that you are clicking the photograph and you actually see your mass in the mean position. So it was like a classical analogy. But in first excited state, you can never, even if you take the 1 million photos or 1 million observations of the particle, you will never be able to find it in the middle of the well. It The wave function is only telling you about the probabilities. It is not telling you that where is your particle inside, what is he is doing, what is actually happening. It is only telling that when you will actually try to measure the particle, most of the times you will find it here, here, sometimes you will find it here, sometimes here, and never here. Similarly, in the second excited state, there are three equal probabilities that it is maximum probability that you find here, 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 and you will never find them here. So try to imagine that there is some quantum intensity inside the well, and it never sits at this spot or this spot. Okay, never, never, ever. If it has energy 4 E naught, it will never sit in the middle. If it has energy 9 E naught, it will never sit at these two x values. So this is what your wave function is telling you, that this is a way you can actually look your wave functions. Now, another thing I want to mention here, one more thing. So this was your what we plotted wave function or energy eigenstate. Now let's plot wave function mod square, means phi square, which actually tells us about probability. It was probability, phi is actually probability amplitude. So now you know the probability can always be positive or some. Okay, so how you plot it? You plot it like this. Okay, so you understood that this assignment, that how you do it. So now your question for you, my question for you is, go home and try to plot phi 4, similarly phi 4 square, phi 5, and up to phi 6. Similarly do this. It will give you a little bit an idea that how to plot it. And remember that you have to satisfy node theorem, that if you are plotting n phi 6, you must have 5 nodes between the well. The 2 nodes which are on the ends, don't consider those. Okay, so whenever you see a wave function, do not picturize your entity as a wave. Okay, instead try to imagine it as a probability. This is how you read the quantum. Because of this lack of ability, students find quantum mechanics difficult. So this is how you read the quantum mechanics. Now I discussed till now about the eigenstates. Eigenstates are just like the unit vectors in the uh, vector calculus we discussed. So you know, in vector calculus in Cartesian systems, I, J, K are the unit vectors. So if there is like infinite dimensional space, then you will need more, like let's say alpha cap, beta cap. There will be like infinite number of unit vectors. In 3-dimensional, there are only 3 unit vectors. So whatever is a task of these unit vectors in the your classical Cartesian systems or vector algebra or vector space, the same thing your eigenstates are doing in quantum mechanics. Okay, how? Let's talk about it. So quantum mechanics is a very interesting subject. Quantum mechanics says actually one thing, that until unless you observe your system, It can be also, it can also be in superposition of the eigenstates. It can also be in superposition of the eigenstates. What does it mean? I am saying that your system can either take value E0, 4, E0, 9, E0, and so on. But no, quantum system says that until unless you measure it, it is actually in the superposition of all these states. It is somewhere, it is somehow have some energy E0, it has some energy 4 E0. It's a very wrong analogy to say that it has some energy E0 or 4 E0. Just for understanding, I'm saying it is in the superposition state of phi 0, phi 1, phi 2, phi 3. We do not know until unless we measure it. Okay, so let me simplify this concept. One is eigenstates, which we have find phi 0, phi 1, phi 2, phi 3. Second is state of system, that in which state your system is actually in. So let's define it by phi. And this system can be in the superposition of this all eigenset. It means it can be in like alpha phi 0, beta phi 1, gamma phi 2, and so on. What does it mean? It is simultaneously in all the states. Simultaneously in all the states. But once you do the measurement, you won't find it simultaneously in both the states or on all the states. If you do not measure it, it is behaving like, the correct statement is, if you do not measure your quantum entity, it is behaving, not it is in, but it is behaving like it is in the superposition state of all the eigenstates, or maybe 2 eigenstates, or maybe 3 eigenstates, or maybe 4 eigenstates. So it can be in the superposition of eigenstates. So how your phi 0, phi 1 was acting like I1, I cap, J cap? Because you know in vector algebra, how do you define your 2 I cap, 3 J cap? So similarly here we are defining our general state or the state of the system like this only. Na? So what is your phi 0, phi 1 acting like? It is acting like I cap, J cap. This is what I was. Okay, so this is your general state of the system, that your state of the system is something like this. So let me very formally put it so that we can actually do it. Let's put it the right words. So alpha naught, phi naught, alpha 1, phi 1, so on. Or we can write it as alpha n, phi n, where, oh sorry, naught is not there. No? Phi 1, phi 2, phi 1, phi 2, and n is from 1 to infinity. This is how you can write your general state. So what will happen after the measurement? So before measurement, we understood that if you are not measuring, we are not disturbing our quantum entity, it can be in superposition of the state. So is there any rule for this alpha n? Yes, there is one rule. The rule is you have to satisfy normalization condition. Normalization condition. What is that? Phi star into phi must be equals to phi star into phi must be equals to 1, and you have to satisfy this condition. How do you satisfy this condition? So I will give you 2 examples first and then you will tell you. So let's say one general state is this: root 0.6 phi 1 plus root 0.4, and second example I give you is 2 phi 1 plus phi. Okay, so by looking at these two, both looks like that it is, our system is in superposition of, sorry, here phi 2. Our system is in superposition of state 1 and state 2, eigenstate 1 and eigenstate 2. But are these both the valid general states? No, one of them is not. And how to check that? We have to satisfy the normalization. Let me keep the notations. Perfect. So phi star into phi. Let's do it. So this is how you do it. Under root 0.6, phi 1, phi 4, phi 2. How you do it is, then you get phi 1 star into phi 1. Something here, some constant here, phi 1 star into phi 2, 0.4, phi 2 star into phi 2. Again, some constant here, phi 2 star into phi. Now I want to make sure that you know that your eigenstates are normalized. Your eigenstates are normalized. If your eigenstates are also normalized, then your phi 1 star and phi 1 must be equals to 1. Similarly, your phi 2 star into phi 2 must be equals to 1. Second thing which I want to make sure is, here you should write that eigenstates are normalized. Second thing is, your different states, your different eigenstates are orthogonal. If phi 1 and phi 2 are acting like I cap, j cap, so if you take their dot product, it should give you 0, or you say that they both are orthogonal. So whenever they are orthogonal, it means that your phi 1 star into phi 2 is equal. Phi 2 star into phi 1 equals to 0. I will come to this point more, but for now, just please trust me and uh, believe in this point. First point, you can easily believe that they are normalized, so they are, your individual eigenstates are also normalized, so that is a reason that your phi 1 star and phi 1 should be 1, and similarly phi 2 star and phi 2 should be. So what do you get? Then what you get? Phi star into phi, when I did, or here if you see what I get 0.6 plus 0.4 equals to 1, which is perfectly alright. Perfectly alright. But if I do second thing, na, for this state, if I will find phi star into phi, I will get 2 square plus 1 square, which is actually 5, which is not equals to 1. It means it is not satisfying the condition that maximum probability can be 1, or the sum of the probabilities can be 1. So this is a situation where this cannot be correct. This cannot be correct. So how I make it correct? How I can make this uh, state correct? You just need to normalize it. So whatever I'm getting 5. So what you do is you divide it by root 5. You just divide it by root 5 and you do it phi 1 plus phi 1. So now it is correct. Now if you will not try to normalize it, it will give you the answer 1. So this is how you normalize it. So what is the condition if my general state is this? If my general state is this, then the condition is it must be equals to all the coefficients which you have, take their complex square, and that complex square, if you add them, it should be 1. So now the question for you is number 1 question, which will directly come in jam. So please solve it. Number 1 question for you is, I am giving you one state, root 2 phi 3 plus root 2 phi 4. Is this a valid journal state? And if not, how do I make it valid? What should I divide? So let's make it more interesting. First is root 2 iota, and second is only root. Now let's do it. So the situation is alpha 1 star into alpha 1 summation should be equal to 1. So let's talk what is alpha 1 star into alpha 1 plus alpha 2 star into alpha 2 should be equal to 1. So what is alpha 1? It is root 2 into minus iota, because now I am doing complex quadrant. Similarly, root 2 iota. Now root 2 into root 2. What is actually I am getting root 2 into 2, 2, and 2. I am getting 4. Is this correct? I am getting 4, or anyone else is getting anything else? Is the 4 good correct answer?
Yes.
If I do 5 star into 5, I will get 4. But what should I get? 1. So what should I divide it with? Here is the question. What should I divide it?
1/4.
But
We should multiply 1/4.
no, not 1 by 4. But 2. 2. Yes, right, Ayushi. 2. You have to under root it and then divide. Okay. Understood? You should divide it by 2. Because you are squaring it. Na? While normalizing, you are squaring it. So then after squaring, it should become 4. So now it is a correct state. So 2 things always you should remember. It is a complex product. Means 5 1 star into 5 1. Okay. Oh, sorry, alpha 1 star into alpha 1. So whenever iota is given, don't forget to take minus sign with that. Otherwise, you will make a wrong. You give a wrong answer. That you should keep in mind. So now tell me, what does this equation tell you? That your system is in superposition of third and fourth state. Okay, third and fourth state. So now once it is clear that what happens before the measurement, now comes after, and it is very important. And I will consider this as a journal thing, that this is our example. So let's do everything with an example. We are taking that example is that this is our general state. Or we can also write it like this. Okay. So my system is in superposition of third and fourth state. What will happen if I do the measurement of the system? What measurement? First thing to answer is what measurement? Energy measurement. First thing to do is energy. Why I have started with energy measurement? Because I already have my state, my journal state in terms of energy eigenstates. Energy eigenstates. 5 3 5 4 are energy eigenstates, and I have written my journal state as the in terms of the energy eigenstates. So let's do the energy measurement. So if you do the energy measurement, there are two possibilities. Either you get energy E3 or you get energy. You will never get energy E1, you will never get energy E2, E5, E6, E7. No, because your system, your particle is in the superposition of phi 3 and phi 4 state. So if you do the measurement of E3, oh sorry, energy measurement, you will either get E3 and E. But you can't get both together. You will either get E3 or you will either get E4. It is like a coin toss. You toss a coin, either you get heads or tails. You can't get both. So there are different probabilities of getting E3 and E4. What is the probability of getting E3 and what is the probability of getting E? That we need to find. How do we find that? What we do is we see what is the coefficient of the state phi. So what is the coefficient of state phi? Iota by root. What is the coefficient of state phi 4? It is 1 by root. Now we know so we now do phi 3 star into phi 3, which is actually 1 by 2, and similarly phi 4 star into alpha 4 star into alpha 4, it is 1 by 2. Now you know the sum will be 1 because it is a normalized state. We already normalized it, so sum will be definitely be 1. So what is the probability of getting E3? It is alpha 3 star into alpha 3 divided by alpha 3 star into alpha 3, alpha 4 star into alpha 4. sum should be this sum should be 1 because we already normalized it. So it is only alpha 3 star into alpha. So the probability is half. Similarly, the probability of E4 is also. So 50% of the times you will get 1 by E3, and 50% of the time you will get 1 by 2 or E4. So half times you will get E2, oh sorry, E3, and half times you will get. So if anyone gives you any general state, so let's discuss one more question. So for your practice, so if anyone gives you any general state, like I am going to give you right now, so this is your general state. Yes. So this is your general state. It is a superposition of phi 1 and phi 2 state. And now I am asking, what are the two possible values of energy that you can get? If you do the measurement of energy, what are the two possible things you can get? Yes, E1 and E2. Either you will get energy E1, which is pi square h cut square by 2 ma square, or either you get energy 4 times pi square h cut square by 2. So what is the probability that you get energy E1? Find it out very quickly.
3 by 4.
3 by 4, or what in percentage, what is that?
74 by 75.
75%. So 75% times you will get energy E1, and 25% of times you will get energy. How many of you got this? 75 and 25%. It is very important that you understand this. How many of you understood this? Tell me very quickly. You can speak up. You don't have to raise the hand. I can hear your voice. I love to hear your voice. बताओ बोलो. Unmute and say yes.
हाँ भैया.
There is some energy. बहुत आलसी बोल रहे हो.
Yes.
Very good. Energy लेकर आओ. Very nice. So if you understood this, I am glad, because this is going to give you marks in exam. Now the question comes that after the measurement, I told you that this should be the energies, and this is the probabilities of getting any particular energy. But what is a wave function after measurement? What is the wave function after measurement? This is my question to you now. Before measurement, we know this is our wave function, or this is our state. This is how we are describing the state. But what is the wave function after the measurement? So your wave function collapse to an energy eigenstate. So please write it along with you. Wave function, write it, wave function collapses after measurement to the eigenstate corresponding to the energy value, which we have got. So do not worry if you have not understood. I am just explaining. So let's say you found that you have got energy E1. So your state after the measurement will be simply phi 1. And if you have got E2, your eigen or your wave function or your state of the system will be simply phi 2. So before the measurement, it was a superposition of phi 1 and phi 2. But after the measurement, what will be the wave function, or in which state your system will be? It will depend upon what answer you have got of your energy. If you have got in E1, then your state is phi 1. If you have got E2, your state is phi 2. So it is also called wave function collapse. Wave function collapse. So superpositioned wave function become the eigen function, because these are the eigen functions. So till here, It is a one part. Now we will be moving to second part. That is why I'm asking. Is it clear till here what we have learned?
Yes, Bhaiya.
Yes, sir.
Yes, sir.
So the second thing now I want to discuss is very, very important and direct questions. I can give you in written that one question from JAM is going to come, and for GATE also the questions will start from this basic information. The first information I told you that if you have the phi means this phi, which is written in terms of eigenstates, you can find anything. You can find x, you can find momentum, you can find position x, you can find momentum, but how do we find all this? So we usually find the average values. What we find is average values. So before coming to the average values, let me define one quantity which is called inner product in quantum mechanics. So the inner product of two wave functions or two states, let's say phi and phi, is simply phi star into the integration over the entire limit. Okay, this is the definition of inner product. In inner product has the same meaning as dot product has in your general vector algebra language. So let me give this more meaning. Number one point regarding this comes as what will be the, let's say these are your states phi 1, phi 2, eigenstates phi 1, phi 2, phi 3, phi 2. So number one thing is if you do the inner product of phi 1, phi 1. So I want you to look phi 1 as I cap, phi 2 as j cap. Just look, they are not I cap, j cap. Just look it like that. Only imagine them like I cap, j cap so that you can answer these things. So if I dot product of I cap with I cap, what is the answer that you will get? What should be the answer?
1.
Yes.
1.
Similarly, if you do phi 2, what should be the answer? So this is called the inner product with itself, or called the, simply we call it like norm. When you do the inner product with itself, it is called norm. Okay, since these are eigenstate, not the wave function or the general wave function. These are eigenstates. They are very simply they are unit, means they are unit vectors. Like you can say they are unit vectors in quantum. What is phi 2, phi 1? If the two states are orthogonal, what is the meaning of orthogonal in quantum mechanics? In linear algebra or in vector calculus, you know the orthogonal means both have 90-degree angle. But what is the meaning of orthogonality in quantum mechanics? The meaning of orthogonality in quantum mechanics is if you are in state 1, then you can't be in state 2. Means if phi 2 and phi 1 are orthogonal, it means if you are definitely in phi 1, then you can't be indefinitely in phi 2. Okay, do not confuse it with phi that I said that they can be in superposition of phi 1, phi 2. Don't confuse it with this. I am only saying that these two are the independent states. Means after the measurement, if you are in phi 1, you can't be in phi 2 after the measurement. So you can't do like that you measured anything and you get both of them. This can't happen. This can't happen. You can't get both of them together. So they are like independent states. Yes, our system can be in simultaneously in both of them before measurement, but not after. So they are independent. So it is a meaning of orthogonality. Okay, this is a meaning of orthogonality in quantum mechanics, and simply you know that in infinite potential well, all the states like phi 3, phi 1, all of this will give you the zero answer. Okay, or simply 5351 will give you 0. This is a thing which we used in the last page when we were doing the inner calculations. Now comes the very important part. Very important part, and many times I have seen the question have came from this. So now I give you a general state phi root 3 by 4 phi 1 plus 1 by root 4 phi. Now I ask you to do this. Now I ask you to do this. So how do you do this? You do this like phi 1 star into phi. So what is phi 1 star? Phi 1 star is phi 1 star. Let's put phi value here. Phi 1 star into phi 1 and 1 by root 4 phi 1 star into phi 2. So this will be 0. This will be 1. Root 3 by 4. Root 3 by 4. So what does this quantity represent, my brother? My brother, what is this quantity represents? Let me give you an analogy. Let's say A is an vector which is root 3 by 4 I cap plus 1 by 4 j cap. If I do A cap dot I cap, I will definitely get root 3 by 4. What does it represent? How much of your system is in I cap or towards the x-axis? Similarly here, what does it says? Your system is in superposition of phi 1 and phi 2. But how much of your state is in phi 1 and how much of your state is in phi 2? So how many of you understood this analogy and the meaning of this quantity? No one?
Repeat, please.
Repeat. Okay. So phi 1 and phi 2 are the eigenstates which I told you are acting like I cap and j cap, like in vector. If I do the dot product of this phi with any of the eigenstates, let's say phi 1, like here I did phi 1. So I get phi 1 star into phi 2 and I get the root 3 by 4. So this is actually telling me how much of my state, means my phi state, this is in the superposition of eigenstate 1 and eigenstate 2. But if you do this, if you calculate this tells me how much of your this state, your general state, is in eigenstate 1. How much? It is root 3 by 4, or you can say 75. Similarly, if you do phi 2 into phi without doing any calculation, you can say you will get value 1 by 1. It is simply like it is an A vector, and if you dot product with it I cap, you will get to know that how much of your vector is along x-axis. How much? Root 3 by 4. And how much is your vector is along j cap? You will get 1 by root. So this thing and this thing are equal. So in quantum mechanics, this is a meaning of this quantity. Now, do you understand?
Yes, Bhaiya.
Yes, sir.
So let's move on. Or should we not move on? So I think we should not move. The reason being, I want to go slow. Tomorrow what we will discuss is very, but we will find how can we find the average value of position and average value of moment. So let's say I say that your system is in this state. Again, I'm taking the same state. Okay. So if I take the measurement of position, till now I have taken the measurement of energy, but now if I take the measurement of position, what will I get? What will I get? Where will I find my particle? Or if I take the measurement of momentum, where I will find what momentum I will get? Or can I get the actual momentum? Or do I need to find the average momentum or average position? This is what we will do. This is what we will, okay, tomorrow. That how to find average position and average moment. And then we will shift from infinite potential well and do the other questions of quantum mechanics based on the knowledge of quantum mechanics which we have gained from the infinite potential, that we have learned how to normalize, we have learned how to find average positions, we have learned how to find the eigenstates and so and so on things, and then we will use this knowledge and find the and apply it to the different quantum systems. So tomorrow we will do that. So today let's end the lecture. I will suggest that please watch these lectures 3-4 times, because these lectures are actually the foundation of quantum mechanics and it usually takes some time to get an understanding of that.